So at the beginning, short introduction to magnetoimpedance. Magnetoimpedance corresponds to the change of real and imaginary part of complex impedance of ferromagnetic conductor when this conductor is exposed to static magnetic field. Usually, the GMI effect is observed at the relatively high frequencies when the penetration depths, or we can call it skin depths, is smaller than the sample thickness. In this case, the applied currents flows in the shell close to the surface of conductor. And the skin depth is given by this formula. We can see that here we have frequency, here we have conductivity, electrical conductivity, and here we have permeability. So as for soft magnetic materials with high permeability, we can see that this thickness or this effect could be observed at lower frequencies as for materials with low permeabilities. And actually, the role of static magnetic field is to modify the value of permeability. So we can see on this slide, on this picture, when we increase the DC magnetic field, then the permeability will decrease and penetration depth will increase. So by this way, we can change the magnetoimpedance. And here is some kind of geometry of this experiment. Here we have the sample. The AC current is flowing through the sample. It creates HC magnetic field in perpendicular direction, and DC field is applied. And by this way, we observe this GMI characteristics, which the most important is so-called GMI ratio, which is given by this formula. And for sample with longitudinal magnetic anisotropy, we observed this one peak behavior. For the sample with transferred magnetic anisotropy, we observed this double peak behavior. What is for sensing properties the most important is the field sensitivity. It is given by the maximum field sensitivity is in the position where the maximum slope of this curve is observed. In this case, it's here, or in this case, somewhere here. Yes, but what is also important that this kind of sensors are used for measuring of very low magnetic fields. And we see that at zero field, we have the sensitivity will be low because we have peaks there. So it's good to shift these characteristics. Usually it is done by applying some bias DC field, that the working point close to zero is shifted somewhere here. Then we have high sensitivity. Okay, so now we can go to first part, and it will be a preparation of, firstly, a preparation of this rapidly quench ribbons, and then how we can use them for GMI. So it's the geometry of the system that we will speak about is following: that we have one ribbon, one layer, and on the top of this ribbon we deposit another ribbon or layer. So that in this case, this is one ribbon with two layers. Yes, that and there exists a solid interface between them. So it is possible. Our colleagues in Bratislava succeeded to prepare even three ribbons, three layers. So it is some kind of additive manufacturing. Yes, that we deposit one layer, then another layer. But it's in the case of amorphous, it's not possible to make very thick or bulky structures, because we should keep in mind that all layers should be amorphous. So, and this is the experiment. Yes, here we have for preparation of the layer, we have crucible that is divided to two chambers. Each chamber has its own nozzle. Then this melted alloy in this chamber is ejected on the rapidly rotating copper wheel. It is immediately solidified, and on the top of already solidified ribbon is from this second chamber, which and nozzle is very close to this, is ejected another melt, and so that it solidified on the surface of the previous layer. Yes, that. But as already I mentioned, we should keep the conditions that there is sufficient cooling rate also for the second layer. The typical cooling rates are somehow in the range of 10 to 6 Kelvin per second. So that it is not possible to make really many layers, yes, because the outer layer, when we have already more layers, will be not cooled by sufficient rate. Okay, now we can have a look on the morphology of such layer after preparation. In this case, it is layer of fine mat, which is this layer, and the upper layer is fine mat without copper. So in this case, copper is very important for making nanostructure in these materials, because copper is not soluble in iron, and it creates some clusters which are seeds for nanocrystals. So when we have even such small amount of copper, we have very high nucleation rate. Without copper, we have not so high nucleation rate, and the structure is more rough. It means we have a bigger grains. Here we have in higher magnification, the interface between these layers is very sharp. We can see it, and here we see how it is. Here this fine mat layer it exhibit very fine grains. It means around 10 microns, and this layer is exhibit bigger grains. So here we see that the bigger grains in such a case means that the structure is not efficient enough to average out magnetocrystalline anisotropy in according with Herzer model, and the coercivity will be higher. So we see that such delayer ribbon exhibit kind of two coercivities. One is here, it's fine mat, and another one somewhere here. It's this layer with bigger grains. So we have something like soft hard, or in this case we can call it semi-hard, because it's not really very hard material. So that we made with our colleagues in Spain for analysis of such systems, and it was shown that this layer, soft layer, is influenced by hard layer, and there is some kind of magnetostatic bias acting on soft layer from hard layer. I will show you it in other system in more detail. Here we have GMI characteristics of such layer. You see that in the case of fine mat, we have quite good magnetoimpedance ratio, but in the case of this harder layer, of course, this magnetoimpedance is lower, because we have here much lower permeability. Okay, here is another system which we develop later, and here it's even bigger difference between soft and hard. Here we have soft magnetic fine met, and here we have, after crystallization of this cobalt-based amorphous ribbon, we have bigger grains. We can see it already here that the grains are really much bigger than fine met, and in such a case, the coercivity of hard layer is in the range of something like 200 Ersted, while in the case of fine met we have excellent soft magnetic material. But um, in this case, we can observe quite interesting phenomenon, and this phenomenon is so-called, we can observe really effect of magnetostatic bias from the hard layer and we can see the shift of hysteresis in comparing to the origin. So in this case, the shift is something like 5 Ersted, and the experiment is as follows. We apply firstly the field of 500 Ersted, that the hard layer is saturated, and then we decrease the field to 0, and we do hysteresis loop in the range of minus 50 to 50 Ersted. Such a field is not sufficient to change magnetization of hard layer. So hard layer is always magnetized in this direction, but soft layer is we can magnetize it in both directions. But if we look on this, the kind of dipolar field from this semi-hard layer is close through this soft layer, so it's playing in opposite way as, for example, here when we have external field in this direction in positive, the bias field is oriented in negative direction. And here we have this situation that the external field, which is positive, is smaller than bias field, which is negative, and even if the field is positive, we have negative magnetization. So this is kind of explanation of this shift of hysteresis loop. And this can be used for tuning the position of GMI ratio curves in both directions. So if we apply field of 50 Ersted, 500 Ersted in positive direction, it is shifted into positive. If we apply to negative way, it's shifted to negative. Yes, that. So by this way we can apply some kind of bias field to also to this magnetoimpedance curves. The second part of my talk will be devoted to the study of effect of ribbon thickness. In this case, we have prepared 3 ribbons of amorphous structure with this composition. And here there is a single layer ribbon with thickness of 22 microns, double layer with thickness of 38 microns, and three layer or triple layer with thickness of 54 microns. But the composition of each layer is the same. So we can study here the thickness effect. Yes, that we did here also annealing after preparation to make some kind of stress released annealing in order to improve magnetic softness, because in this case of material the main factor is the magneto-elastic anisotropy, and when we decrease magnet stresses, then this factor is somehow diminished. here we see that all single layer, bilayer, three-layer samples were amorphous. This is X-ray was done on the top layer. It means the layer which or the side which was the most distance from the wheel. And what was interesting, we have observed here extremely low coercivities, but the coercivity was lower and lower with increased thickness. So it was kind of puzzle or puzzling behavior for us. Why it is this behavior? Because it's really this coercivity is 0.3 amps per meter. It's really excellent value of coercivity for submagnetic materials. And the explanation was we somehow considered that this system could be a nice system for proving the prediction of all prediction of Professor Kronmüller. You see this very old paper. He somehow analyzed possible contributions of different factors to coercivity of submagnetic materials, amorphous submagnetic materials, ribbon, in the ribbon form. And he showed that there are some contributions that are not visible normally because the magnetoelastic contribution is so high that it's much higher than these contributions. But he considered that there is a contribution from the surface roughness of the material. And this contribution, of course, could be observed only when the coercivities are extremely low. And somehow the physics behind this is as follows: that when we have here domain wall tend to be stabilized in the position where its area is minimal. So when we have here some kind of roughness, it will prefer to stay at this position, and to shift it to increase the surface, we should apply additional magnetic field. And this contribution is as follows. Here, this one is average thickness, and this part is the maximum surface gradient, average maximum surface gradient. If we consider that the surface is of this single layer, bilayer, three-layer, the roughness is comparable, then of course coercivity will scale as 1/t. It means thickness of ribbon, what we observed in our case. And here we see how is the effect of thickness, different thickness on GMI. Here we see that GMI effect slightly increased with thickness of ribbon. But what is interesting that the maximum of this GMI response is different, is observed at different frequencies. Here we can see it's somewhere between 2 and 5 megahertz. Here in this case it's somewhere between 1 and 2 megahertz, and here it's probably below 1 megahertz, and we can see it in more details here, that really with thickness of ribbon we have shift of maximum of GMI to lower frequencies, which of course can be somehow explained by the fact that in the case of thicker ribbon, the condition that this penetration depth is lower than the thickness of this ribbon is fulfilled earlier in the thicker ribbon. It means in three-layer ribbon, so the magnetoimpedance starts to grow at lower frequencies. We did in some of our older paper also such studies for Feynman materials. And here it's also we can see beneficial effect of thicker ribbon. It means in the case of bilayer we have higher magnetoimpedance response, and we have also higher sensitivity. So it's good for sensing properties. And the last part of my talk, sorry, I will look how much. Oh, okay, still some time. The last part will be devoted to tailoring of GMI characteristics by application of magnetic field during annealing, so-called field annealing treatment of materials. So here there are some facilities that we have in our lab. In the case of soft magnetic materials, of this case of nanocrystalline and amorphous, that is sufficient to apply lower fields. I will show you why. Because when we apply the, here there is domain structure of material of this composition. And when we anneal it at temperature which is lower than Curie temperature, this domain structure still persists. So we do annealing and magnetic state of sample is very complicated. By this way, domain walls and domains are somehow stabilized in the position they occupy during annealing. When we apply the field during annealing, all domains are somehow wake up. We have homogeneous situation. The sample is homogeneously magnetized, and we apply the somehow induce anisotropy in one preferred direction. So when we decrease the field, domain structure is like this. This is possible for goods of magnetic materials. Actually, after such field annealing, this field-induced anisotropy is dominant factor, which influence the magnetic behavior because the other anisotropy are small. And we see that after application of such treatment, we can have very different hysteresis loops. Everything was the same, only field during annealing was applied in different directions. So if it was applied in longitudinal direction, we have this pretty square hysteresis loop with extremely low coercivity. When it was applied in the transverse direction, we have this linear loop with rather high anisotropy field, and it is done by the fact that here in this case of longitudinal, we stabilize such domain structure. Here we have magnetization by moving of 180 domain walls, which is easy process. Here we need to apply higher field because in this case it's rotation of magnetic moments to the applied field direction. So we see that it's really for this sample we have domain structure in this after longitudinal direction and perpendicular to the field here. This is the applied field during measurement. Okay, so now I think I should already speed my talk. Our goal was to look for material which will be good for GMI sensors, which will be stable at high temperature. So one of our previous work, we have the results that when we add cobalt to this kind of composition, we increase Curie temperature and magnetization and as well coercivity are stable to high temperatures. In this case, we use even higher cobalt concentrations. You see that we prepared one sample was iron-free. It means it was cobalt niobium boron type, and here we have some iron. Here it is kind of FCC structure here is BCC. In all cases, we have very nice small grains. And here, it's in this case, we see that domain structure, as was already discussed, hysteresis loop in accordance what could be expected after longitudinal and transverse field annealing. Here at GMI, what is interesting that really what is observed or discussed before, after longitudinal field annealing, we have single peak GMI. After transverse field annealing, we have double peak. The intensity of this GMI response increased with addition of cobalt. We then for GMI at high temperature, we developed this facility where the sample was in evacuated furnace, and field was applied to by this kind of Helmholtz system. And you see that after application of temperature to this sample, cobalt base, which exhibit the highest GMI, we see really very nice stability of signal. So by increase from room temperature to 300 Kelvin, we see nearly no change. In the case of transverse field annealing, we see some change, especially there is a low decrease of anisotropy field, but the steepness remains more or less constant, and we can see it better here. So, and I would like to mention that even after longitudinal field annealing, the stability was better, but the sensitivity was very low. In the case of transverse, the sensitivity is much higher, so it's better for sensor. And we did also measurement of kind of aging effect. It means we applied the temperature 300 degrees Celsius for 12 hours, and we see that this is very good stability, so that it means nearly nothing change, so that this kind of material can be applied for a long time at elevated temperature. So, and this is the end summary of my talk. I think, yes, I was just in time. It was shown that it's really this double nozzle or triple nozzle technique is good for preparation of this B-layer and S3-layer, and these systems can be interesting for GMI. And in the case of these cobalt-rich iron, cobalt, niobium, boron ribbons, we see that they are promising candidates for GMI sensors that are capable of operation at high temperatures. So thank you for your attention.
It was interesting to see when the thickness of the ribbons increases, the coercivity decreases. Can we use such kind of ribbons in the flash gate sensor as a flash gate sensor if the magnetic permeability is high and the saturation field is around 1 Tesla, like that? I'm not sure. I want to learn your opinion.
Yes, of course. I think it will be possible, but in this case of material, we have there quite higher amount of nickel. You know that in this case the saturation magnetization is lower. And of course, when you do annealing of these materials became to be brittle. You know that there is also problem to somehow to deal with this brittleness, because you should manipulate with the ribbon, and I think that what is our opinion, some kind of experience, that these thicker ribbons, they are somehow more brittle. it's more difficult to handle, to bend them or something like this. But I think it could be interesting because really that softness is much better.
Maybe
it's extremely good.
For the ring core geometry, for example, maybe after wrapping the ribbon, and then annealing may help us.
I think it would be possible to do firstly in amorphous, and then, but that's for this kind of 3-layer is not easy to prepare very long ribbon. I think, but they are pieces. Some it could be some 1 meter or several meters even.
1 meter.
Depending. Yeah, I know. 1 meter will be enough. Yes, that.
Yeah. 30 centimeters is also enough for me.
Yes. Okay, so maybe we can discuss this.
Okay, thank you very much again for participating and sharing your valuable studies with us. Thank you very much, Ivan.